This leads us into one of the most interesting of the organic chemistry molecules as far as I'm concerned. You can make a cyclic structure, so 6 carbons, if you will, in this case, in like a circle, all right? And you can have alternating double single, double single, double single bonds. So it's kind of like a cycloalkane, but it's with an alkene, and there is a type of a family of compounds called cycloalkenes. However, in the right combination, and this one is an example of that, those alternating double single bonds create a type of a ring current because resonance allows the double bonds to trade places, like they all rotate by one bond. And the resonance like goes on and on. So they rotate by one, then they rotate by a second, then they rotate by a third, and they go on and on and on. So sometimes you'll see this type of structure written as 6 carbons with just a circle in the middle of it. And the circle is basically a way to represent the resonance of it. So sometimes those double bonds, when they're conjugated, which means alternating double single bonds, you get an increased stability. And if you end up with this kind of combination, you have what's called an aromatic hydrocarbon. And aromatic compounds are especially stable, and they have real special kinds of reactivity. This is a really interesting, in my opinion, part of organic chemistry. There's a lot of information that we're not going to talk about in relationship to aromatic compounds, but we're going to talk about the simplest of the aromatic compounds, which is called benzene. And benzene is literally 6 carbons in a circle. You have alternating double single bonds. They will resonate, they will rotate around each other, and you end up with this wild kind of ring current. You can see that the molecule is flat, and the flatness does create some special reactivities. Like some of the reactivity that you expect for an alkene doesn't happen with an aromatic compound. And sometimes aromatic compounds will react in ways that the alkenes won't. It's a real interesting kind of phenomena. These pictures here show the different types of electronic networks. The upper left one is just the sigma bonds, all right? And again, sigma is the head-to-head overlap between carbons and stuff like that. The lower left one shows the pi bonds. And again, back to our discussion from the last chapter, pi bonds are kind of like the bread of a sandwich, and the sigma bonds are kind of like the quote-unquote meat that goes in the middle. And then the upper right-hand picture shows the bread and the sandwich all together. It's making me hungry. I shouldn't have talked about it. Anyway, Prophet back on. So the sigma bonds are cool, but it's the pi bonds which are really interesting here. You would expect with a regular double bond system, you would just have a little bit of pi bonds like here and there, like alternating, but they don't. They resonate like crazy. So it creates that kind of donut looking thing, which is literally the pi bond kind of running around and around and around in a circle. And they've measured these kind of ring currents in the molecules, which are very, very interesting. But the ring current does create a special kind of stability and reactivity that you don't see in other molecules. So basically it's the pi bonds, those pi electrons, that create the aromatic stability, which is really cool. In organic chemistry, this is a fascinating area of research, I think. A carbon-carbon single bond is about 154 picometers, and a carbon-carbon double bond is about 134 picometers. So remembering how as bond order goes up, the bond length goes down. So bond order 1, carbon-carbon single, and bond order 2, carbon-carbon double, you can see how bond lengths are certainly decreasing. Well, in benzene, the carbon-carbon bond length's 139 picometers. Now, technically, we would think of the carbon-carbon bond order as not 2 or 1, but kind of a hybrid because these are resonating around. So instead of having doubles and singles, you would expect the bond order to be about 1.5. More than a single bond, less than a double bond. However, because 139 picometers is pretty close to 134 picometers, there's something else going on here. All right, the resonance in an aromatic compound is like an extra level of stability, making it a little bit stronger. So this delocalized pi network is very, very cool, and that's a direct result of the resonance in aromatic compounds. You can place different pieces on a benzene ring, and they have some special names. We're going to talk about these more in lecture and also in the organic chemistry lab. If you put a methyl group on a benzene ring, the official name for that would be methylbenzene. However, nobody calls it methylbenzene except for nerdy chemists. Toluene is the name that's usually used. So toluene is just methylbenzene. All right, it's like a common name. Toluene is something that you can buy at Fred Meyer's or Home Depot. It's a lot of times used for taking paint off things and stuff like that. Pretty interesting. In the upper left corner, we have an ethylbenzene, which is just an ethyl group connected to a benzene ring. Nitrobenzene is an NO2 connected to benzene. Bromobenzene. In the upper right-hand corner, an alcohol connected to a benzene ring is called a phenol, and that's something that's kind of cool. Benzoic acid, we'll talk about more in Chem 223. Benzoic acid is a COOH. We'll talk about that more here in a little bit, but benzoic acid. And finally, you can have multiple benzene rings connected to each other. Naphthalene is two benzene rings connected to each other. So you have actually two rings in those guys. It's really cool. Naphthalene has all kinds of different possibilities. So there's lots of examples of these aromatics and stuff we'll see. If two of the positions around the benzene ring have the same kind of substituent, there's a special kind of a naming that's used. And the old way of calling them is by ortho, meta, and para. So what we're seeing here in these examples are a series of dichlorobenzene groups. And in the example on the left, the chlorines are right next to each other. In the middle, there's a spot between them. And in the one on the right, they're opposite. If they're right next to each other, like the first one, then the official name would be 1,2-dichlorobenzene. But you will still see it listed a lot as ortho-dichlorobenzene, or what they usually use is just O-dichlorobenzene. So ortho means 1, 2. I prefer the numbers personally, but ortho, meta, and para you'll see a lot too. Meta means 1, 3. So 1,3-dichlorobenzene is also called meta or M-dichlorobenzene. And para means 1, 4. So 1, 4-dichlorobenzene is the same as P-dichlorobenzene. And you could have dibromos, diiodos, dimethyls, all of those things, OrthometaPara. Again, I prefer the numbers, but you will see the letters as well. Either way is fine.